Hey guys, welcome to lecture 14. Today we will discuss inferential statistics. Everything up to this point so far has been descriptive statistics, univariate and bivariate. Our approach to inferential statistics, we will take the ever popular but somewhat problematic hypothesis testing approach. Hopefully, if you get the chance to take a more advanced class, we will cover some of the problems with hypothesis testing and some of the alternative routes to hypothesis testing. But for today, we'll just cover hypothesis testing. So what are we going to cover? A brief overview. We'll discuss what inferential statistics is. And we did that at the beginning of the year to some degree when we contrasted inferential and descriptive statistics. We will focus on the fact that inferential statistics recognizes the fact that all samples inherently have some error. They will not perfectly represent the population from which they were taken. Inferential statistics relies heavily on probability. We make a statement, an inference. If we state that something is statistically significant, there's always probability involved. We are never 100% certain. And sampling distribution. So inferential statistics relies heavily on probability, relies heavily on sampling distributions, and recognizes that sampling error. All samples inherently differ to some degree from the population from which they were taken. We will talk about some of the uses of inferential statistics, primarily prediction. If I know your ACT score, how well can I predict what your GPA in college will be? We know it is not a perfect prediction. We know there's error involved. And estimation. An estimation can take two forms. We can estimate with a point estimate, a single number. For example, I could tell you that based on a survey of 2,000 people, we estimate that Congress's approval rating is 14%. Or even better, I could probably give you an interval estimate or a confidence interval in some case. In this case, I could say Congress's approval rating is somewhere between 10 and 18% with a certain degree of confidence. We will discuss what statistical significance is. Statistical significance is at the heart of inferential statistics. Just remember, do not confuse statistical significance with practical significance. And I'll discuss that in a minute. We will discuss alpha. Alpha is our statistical significance level, and it will come up later in the second video. The fact that it is also our type 1 error rate. And tied to the alpha level is our critical value, and I will try to explain what these two things are. And then we will discuss hypothesis testing. And hypothesis testing involves testing a hypothesis. And the hypothesis that we're going to test is the null hypothesis. There's also an alternative hypothesis. And I will discuss the difference between these two. But the null, for the most part, always says nothing. There's no difference. There's no association. There's no relationship, at least beyond what you already knew or expected to exist. And the alternative hypothesis, symbolized HA, always states that there is some effect. It's going to be the opposite of the null for the most part. And our hypotheses, if it's the alternative hypothesis, can be one-tailed, sometimes called directional. I expect a positive correlation between study time and grades. Or it can be two-tailed, non-directional. In this case, you don't specify a direction. I think the new drug will impact blood pressure, but I didn't specify a direction. I didn't say it's going to go up. I didn't say the new drug is going to make your blood pressure go down. I just said it's going to change it. It's going to impact it. It's going to affect it. So we'll discuss two hypotheses and the fact that they can be directional. Technically, the null is always non-directional. Technically, it always says there's nothing going on. Sometimes people express it as the opposite of the alternative. So if you have a directional one-tailed alternative hypothesis, they might express the null as the opposite of that. But technically, I will discuss the alternative hypothesis as being one-tailed or two-tailed, and I will just assume the null is always non-directional. One of the advantages or disadvantages of this approach, null hypothesis, alternative hypothesis, hypothesis testing, is it's simplistic. Not that it's easy to understand, but it forces you to make one of two decisions. We're going to reject the null, or we're going to fail to reject the null. Sometimes retain the null. We never accept the null, and I'll explain why that's the case. Just a reminder, we've moved on from descriptive. We're still going to rely on descriptive, but now we're going to take some of our descriptive statistics and we're going to test their significance. We're going to try to make some inference from our sample, which inherently contains some error. We hope it is representative, and we know that random sampling techniques and sample size play a big factor in how representative this is. And then we're going to take our sample and hopefully make an accurate conclusion, generalization, estimation, prediction about what exists in the population. So this is just a reminder, something we covered probably the first or second week, that if we have a summary number, and that summary number comes from our sample, that summary number is called a statistic. If we take and describe our entire population with a number, such as the mean, that summary number is called a parameter. So samples yield statistics, populations yield parameters. And so we discussed a little bit in the past what inferential statistics are, and there's really many different techniques, but one of many techniques that allow us to draw conclusions, generalizations about a population, relying on sample data. Of course, it takes into account random sampling, it takes into account sampling error, it takes into account sampling distributions, it takes into account probability. I will discuss sampling error in another video, but these are probably the three big issues: probability, sampling distribution, and sampling error, and that deals with the representativeness. And the biggest factors of reducing sampling error: getting a larger sample size and using some type of random or unbiased sampling technique. So what is a sampling distribution? So I've given you two examples of sampling distributions down here. This one is for coin flip. If I took a fair quarter and flipped it 10 times and recorded the number of heads, and then did it again and flipped it 10 times and recorded the number of heads, and did it again and again and again, and did this thousands of times, this is what I would expect to see. You're not going to get 10 heads in a row on a fair coin very often. In fact, the probability is so low it's not even registering, but it would be there. It's not zero. 9 heads would be very unlikely. The most likely outcome would be 5 heads. At the same time, you're not likely to get 10 tails in a row, which means no heads in a row very often, if your coin is fair. So if you were to do this little experiment, flip your coin 10 times, record the number of heads, do it again, flip it 10 times, and keep doing this, this is what I would expect for a coin flip, if the coin is fair. If I were to roll a die and record the number of 6s, I would not expect my sampling distribution to look like this. I would expect the most common outcome would be, if I rolled the single die 3 times, to be 0 6s would be the most common outcome. That would occur almost 60% of the time. To get 1 6 would occur about 35% of the time. 2 sixes about 10% of the time, and no 6 or 3 sixes in a row would be just a little over 1 or 2%. This is what I would expect to find if my die is fair, if my die is unbiased. Here is an actual observed set of data. So in this case, the person actually rolled the die and they found about 48, so forth, sixes, no sixes, and about 35, they got 1 6, and out of the 100 flips, they got just less than 20, or they got 2, and when they flipped it 100 times, they got, or rolled it 100 times, maybe 3 times in a row, they got 3 sixes. And so this is what inferential statistics is about. Here's what we expected to get. Here's my sampling distribution. If my die is fair, I roll my die, and I do it 100 times, and this is what I see. It looks very similar to what I expected to get, but it's not identical. So the question I've got to ask is, could this reasonably have occurred from a population distribution that should look like this? Could I take a fair, unbiased die whose distribution should look like this and get a distribution that looks like this with 100 rolls, with 100 experiments? And so this is where inferential statistics would come in. It would give me a probability, a p-value, and tell me the likelihood of getting this given this. So that's just what a sampling distribution is. It's the frequency distribution of a statistic over many random samples. So in this case, out of the infinite number of coin flips that are possible, 1, 2, 3, 4, 5, 50, 10, I've chosen 10, and I do that over and over and over. This is what I would expect. This is my sampling distribution. And if I roll a fair die, or at least what I expect to be fair, die 100 times, statistically, this is what I would expect to get in terms of the number of sixes. And this is just an example of what we actually got. So we're going to compare what we have, what we observed, to what we expected to get based on some underlying sample distribution, based on probability, based on sample size, and so forth. And so this just explains what I said here. What are the uses of inferential statistics? So we mentioned there's 3 big ones. One is prediction. Who's going to win the next presidential election? What's the population of the United States going to be like in 10 years? What's the economy going to look like next month? How many people, new students, will the university enroll next year? That is prediction. In fact, one of the biggest uses of prediction is going to be your insurance company. They're going to use factors such as your age and your gender, and they're going to enter that into a regression equation, and they're going to estimate, they're going to predict how much money you are going to cost them. And so naturally, they're going to use that, and they're going to charge you more over the long run than you are going to cost them, hopefully. And the other one is estimation. So we can say, what is the president's current approval rating? What % of the population has diabetes? Prediction relies heavily on correlation. That's a topic we talked about earlier. And in fact, the stronger your correlation, the more strongly associated your 2 variables are, the better your prediction will be. And that relies on that equation for a straight line that I showed you in the previous lecture. And estimates. So we said we can have a point estimate, a single number. So we could say the president, whoever he or she may be at the time you're watching this, approval rating is 48%. We don't know that. We haven't interviewed all 150 million registered voters, or all 300+ million Americans. So we're estimating what that is. Or I can give you a confidence interval. I can give you a range, an interval estimate. Because I know this is not exact. I know there's sampling error. And so maybe I can say with a certain degree of confidence that his or her approval rating is between 46 and 50%. What is statistical significance? This is one of the single most important concepts that you can take away from this class. And I've found it is misunderstood quite a bit. We put too much reliance on it. It's not that it's important or not important, but it needs to be balanced out with some other factors. So statistically significant means that your outcome did not have a good probability of occurring simply due to chance. It had a low probability of occurring simply due to chance or random error. The problem with this definition of statistically significant is it's got a problematic term, low, or not a good probability. And in science, we can't rely on subjective terms such as low. So we're going to have to define what we mean by this. And I put good, and it should have been low up here. But chance is not a good explanation for your findings. But we have to quantify what is good, how low is low enough. So this is a intuitive definition, maybe something you can understand, a dictionary definition for the layperson. But in statistics, we're going to have to do better. We're going to have to quantify what we mean by good. And we're going to do that with something called our alpha level. So if I give you an example, and I tell you that I am so manually dexterous that I can pick up a coin, I can flip that coin and tell you what side it's going to land on. So I flip the coin and say it's going to land on heads, and it lands on heads. Are you impressed? And I hope you would not be, because the probability is too high. Doesn't mean I don't have the ability to flip the coin and make it land on whatever side I want. But chance is also a very good explanation for what happened. Even if I have no coin flipping ability whatsoever, I could have called that correctly half the time. And so I think most people would agree chance, random error, is a very good explanation for me getting one head in a row. How about two in a row? 0.5 times 0.5. And so I flipped the coin twice, it lands on heads, and I predicted heads both times. Would you be impressed? And again, most people would not be. They would say, well, that's better than once, but 0.5 times 0.5 is 0.25. And so probability is still a pretty good explanation for what you found. I'm not impressed yet. How about 3? How about 4? How about 5? How about 10 times in a row? When do we stop? And each person probably would have their own intuitive stopping point. Some people might say 5, some people might say 10, some people might need more. But in statistics and science, we have to have agreement. So we have to say, what is that good stopping point? And that is where our alpha level comes in. And it should not be a little a, it should be a little alpha. And I think something happened when I converted this. So I will show you what alpha looks like. I did it properly. It should look like this. All right. Not a little a, it's a little Greek alpha. All right, so sorry about that. And so ignore the A, should be alpha. And so alpha level is our statistical significance level. It's the point at which we say chance, random error, probability is no longer a good explanation for our findings. We never say chance or this random error isn't an explanation, but we just say it's not a reasonable explanation. And that's where the alpha comes in. What is reasonable? Typically, it's 0.05 or 5%. So probability 0.05 or 5% or less. So if we get a outcome of 2 heads in a row, 0.5 times 0.5, the p-value, the probability value, the probability of getting 2 heads in a row is 0.25. Well, that's much too high if I have an alpha of 0.05. How about 3 in a row? 0.5 times 0.5 times 0.5. That is about 0.125, 12.5%. Still too high when I'm comparing it to my benchmark, my alpha, which is typically 0.05. It does not have to be. Sometimes you will see it more stringent, maybe 0.01. Rarely do you see it larger than 0.05, but it could be. So this is our statistical significance level. What level of probability is low enough that we are reasonably impressed, that we can say, okay, maybe you do have this coin flipping ability. Chance is no longer a reasonable explanation. Doesn't mean we've ruled out random error, chance. It's always a possible explanation. We can't get rid of it, but we want to minimize it. So it doesn't have to be 0.05. It's a probability value, so it could be anywhere between 0 and 1. 0 would be ridiculous, and 1 would be ridiculous. We need a low value, but if we make it too low, we just ruin our power, which I will discuss in another video. And if it's too high, then you're always going to find some effect. So this is a good starting point. It's like the speed limit of 70 miles on the highway. It doesn't have to be that. Some people want to change it, make it lower or higher. But for this class, most of the assignments and questions will deal with assuming our alpha level, our statistical significance level is 0.05. Now there's a value that is always associated with your critical value or your alpha level. And that depends on the type of experiment that you're doing. So in the coin flipping experiment, there's a certain number of heads that I have to flip and obtain to get my probability less than 5%, or probability less than 0.05 or 5%. And in this case, it actually turns out to be 5. So we said 1 head in a row is 0.5, 2 heads in a row is 0.25, 3 in a row, and so forth. And so if we have 1, 2, 3, 4, probability is still too high. So I need 5 heads in a row, and that would get my probability to less than just a little bit over 3%, which is less than my alpha of 5%. So the value that I must obtain in this particular experiment is 5 heads in a row, because 5 heads in a row has a probability of 0.035, which is less than my alpha level. With the coin flipping experiment or with a die, you can easily figure out critical values. It's just basic math, multiplication. But in many cases, it's really difficult to figure out. I don't know how to do it most of the time. We rely on tables that tell us what the critical values are. So we actually look up our critical value most of the time. Here's an example of a critical value for the Pearson product moment correlation coefficient, or just little r italicized. So if we assume alpha, which is traditionally 0.05, but you can see they also give you another choice of 0.01, and I have 3 pairs of scores, then you can see at the 0.05 level, I really need a perfect correlation before I could find it to be statistically significant. If I increase my sample size, so now I've got 12 pairs of scores, I would only need a correlation of 0.58. And if I got 30 people in my study, I need a correlation of 0.36 or larger to say it's statistically significant. If I increase my alpha, make it more stringent, so I'm being a little bit pickier. Instead of 0.05, I'm going to 0.01. Instead of 5 coins in a row, I'd probably need 7 coins in a row. You can see my critical value, my benchmark, the value that I need to obtain in order to say it's statistically significant, is substantially larger. 0.05 is 0.58 with 12 pairs of scores. If I make it more stringent, I need a 0.71. So the more stringent, the pickier you are with your alpha level, the lower you make your significance level, the more impressive your outcome has to be, the bigger your critical value has to be. Again, with the coin flipping experiment, we could have figured these out with Pearson's R. I don't even think I ever learned how to do and create the table by hand. There was just never a need for it. We typically looked them up, or now most computer packages will give them to you. So back to the coin flipping experiment, we said our critical value, the value we must reach in order to reject the null, the value we must reach to say we have a statistically significant outcome, in this case will be 5 in a row if alpha is 0.05 or 5%, because 5 in a row or more than 5 in a row is needed to get the p-value for our experiment, for our outcome, to be less than 5%. In this case, it's 3%, or a probability of 0.03. So my critical value would be 5 in a row. It just happens to be 5 here, and our p-value is 0.05 or 5%. That's just absolute chance. I probably should have come up with a different study, so you don't assume that your p-value and your critical value or your critical value are going to be the same. They're not. So what is hypothesis testing? Hypothesis testing is one approach to inferential statistics, and it involves testing a specific hypothesis. And the hypothesis that we are going to test is called the null hypothesis. And it has a symbol. It's hypothesis 0, because usually after hypothesis 0, there's a statement of specifically what your null is for your particular study. If I'm interested in studying the effects of caffeine on reaction time, the null hypothesis would be caffeine does not impact reaction time. The counterpart to my null hypothesis, which always states there's nothing going on, there's no difference, there's no correlation, there's no association, at least beyond what you already expected to see. So the null hypothesis is not typically going to say men are not taller than women. It's probably going to say, if we know there's a 5-inch difference, it's going to say there's nothing new about that difference. The difference is going to remain 5 inches. But in most cases, it's just going to say there's nothing going on. Correlation between study time and grades is 0. The correlation between gas mileage and speed is 0. Even though we know those to be false, the null hypothesis is always going to state it as nothing is going on. The alternative hypothesis, usually your research hypothesis, but not always. It's not always what you predict is going to happen, but typically it is. Always states that there is an effect. All right, so the null, no effect. The alternative, there is some effect. There is a correlation between shoe size and grades. There is a correlation between speed and gas mileage. There is a difference in the height between men and women beyond what we expect to see. And so again, it's going to depend on the question that you're trying to ask or answer. It's got a symbol, hypothesis 1, since this is hypothesis 0, or sometimes hypothesis A for alternative. So you will see these, they can be used interchangeably, but the null is always H0. And so, example, if I want to do a study to determine if caffeine improves reaction time, the null is going to be, nope, caffeine will not affect reaction time, or will not improve reaction time. And the alternative, HA, probably should have been a little a, caffeine will affect reaction time. In this case, this is an example of, I actually put, this is a one-tailed or directional. It's not, it's a two-tailed. This is my mistake. I'll correct this in the PowerPoint when I post it. It didn't say how it's going to affect it. So this is actually a two-tailed. It should have said caffeine will improve reaction time. That would have been one-tailed. Caffeine will diminish reaction time. That would have been a one-tailed. But I made a mistake. So this is actually two-tailed, because by saying effect, I haven't told you if it's going to go up. I haven't told you if it's going to go down. So this is a mistake. I will fix this in the actual PowerPoints. Just keep this in mind when you're watching this statement. This is a two-tailed, non-directional, not a one-tailed. And so if I do a study, aspirin affects blood pressure, the null is aspirin will not affect blood pressure. The null is always going to say there's nothing going on. The alternative, HA, aspirin will affect blood pressure. Now I've got a two-tailed. This is correctly stated. I didn't say it's going to improve it. Didn't say it's going to help it, make it go up, make it go down. It's non-directional or two-tailed. This one is not a one-tailed. This is two-tailed. So I should have put caffeine will improve reaction time. That would have made it a one-tailed or directional. Sorry for the error. So just as I stated a minute ago, the alternative hypothesis can be either directional or non-directional. Directional is one tail because we're specifying one tail of the distribution if we got a normal distribution, for example. And non-directional, either tail, left or right, up or down, improves or hinders. And so in this case, let's see if I got this one right. Caffeine will affect reaction. Oh, I did it again. This is not a one-tailed or directional prediction. This is a two-tailed because I didn't say how. I apologize for that. If I used the word improves, which I meant to put, so if I said caffeine improves reaction time, that would have been one-tailed. But this is an error. That's my mistake. And again, I'll fix it. Example 2 with aspirin and blood pressure. Aspirin will not affect blood pressure. That's what the no is always going to say. There's nothing going on. The alternative, aspirin will affect. That is definitely non-directional because I didn't tell you how it's going to affect it. It's not going to go up, not going to go down. Either outcome is okay. If you make a directional prediction, let's just assume this word says caffeine will improve, then it has to come, or the outcome has to be in the direction that you predicted. If not, you're wrong, no matter how impressive the outcome was in the opposite direction. We like one-tailed predictions because one-tailed predictions, directional predictions, are more powerful. It's easier to reject the null hypothesis. It's easier to find a statistically significant outcome if you make a one-tailed prediction. But you can't always make a one-tailed prediction. You have to have a reason to do so. Logic, theory, experience, observation, whatever it happens to be. If not, you should make a two-tailed prediction. But we like one-tailed predictions. One-tailed predictions are more powerful. Power just means it's easier to detect an effect. If one exists, it's easier to correctly reject the null hypothesis. But you can't always have a one-tailed test. Make one. So some people like hypothesis testing, and originally it was employed because it is simplistic. You have one of two choices. You can fail to reject the null, or you can reject the null. That's it. There's no other choices. Some people like that because of its simplicity. Some people do not like being forced to make a dichotomous decision like that when the probabilities can be so similar. But for now, we're just going to stick with the language, reject or fail to reject. And you might ask, well, if we're going to reject the null, how come we don't accept the null? And we never accept the null. We can fail to reject, we can retain it, but we don't accept it. And the reason we don't accept it is because technically the null is always wrong. The null, since it says there's no effect, there's no difference, there's no correlation, technically that's never true. So we know that there is no correlation, no practical, meaningful, real-world correlation between shoe size and IQ. But for the null to be true, the correlation would have to be 0.00000 to infinity. And if I studied thousands of people and recorded their shoe size and IQ, I wouldn't get 0.000 to infinity. I would eventually get some number other than 0, which means technically the null would have been false, even though it would have no practical, meaningful, real-world relationship. So if the correlation between shoe size and IQ is 0.0009, that's meaningless. But technically it's not 0, so technically the null is wrong because the null says it's 0. So we have two choices. I can reject the null. I reject the null if I have a statistically significant outcome. I reject the null if I reach my critical value. I reject the null if the probability of my outcome, the value that I compute, is less than 0.05 or whatever my alpha happens to be. I'm going to fail to reject if I fail to reach my critical value. So I reject my null if I reach my critical value. I fail to reject the null if I fail to reach my critical value. So if you reject the null, that's the same thing as saying we consider the outcome statistically significant. Your outcome reached or surpassed your critical value, which means your outcome had a p-value, a probability value, less than your alpha. And whatever our outcome is, that's what we call our test statistic. That's what we're testing. And so I could flip a coin and get 6 in a row, then I could say, well, 6 is my test statistic. And I could compare that to my critical value, which we already know is 5 based on our alpha level of 0.05. And I can determine, hey, 6 is more than my critical value of 5. I reach my critical value, I'm going to reject the null hypothesis. What we call our test statistic, that's what we're testing. We're determining whether or not it is statistically significant, whether chance is a good explanation for our findings or not. And we're going to compare that to our critical value, or we can find the p-value associated with our test statistic and compare that to our alpha level. And so here, should have put this up a little bit higher in the PowerPoint, you will see it. If I make a one-tailed test, I can put all of my alpha on one tail. And if this were a Z distribution, a normal distribution with Z-scores at the bottom, I would need a 1.645. If I'm doing a two-tailed test, which means I'm going to accept it if things go up or things go down, I still want to keep my alpha level at 0.05, 5%, but I've got to split it because I'm willing to accept this direction, heads or tails. IQ goes up, IQ goes down. There's a positive correlation, there's a negative correlation. I'm willing to take either direction. Because of that, it gives me a little fudge room. I've got to compensate by putting my alpha here and here. It's still 5%, but you'll notice my critical value has gotten larger. It's 1.96 versus 1.645. Smaller critical values are easier to reach. That's why you have more power. So you can think of your critical value as the height requirement at Disney World. So if you're this tall, you get to ride. In this case, I got to be a little taller to ride. So if we reach our critical value, this is our critical region. So anything in this value or greater, if we obtain that with our test statistic, we would reject the null. But if it goes in this direction, we're in trouble. But if we do a two-tailed test, I don't care what direction it goes, but I got to be a little bit more impressive in either direction. So they have advantages and disadvantages. Typically, if you can make a one-tailed test or prediction, do so. They have more power. This critical value is going to be a little smaller. It's a little bit easier to ride the ride. All right. Thanks again for watching. Don't hesitate to call, text, email.